divided by this, so this would be 1 over the determinant of f, f dx divided by the f inverse 1. Okay, so that's the relationship between the density and density of y is the density of x, but evaluated at what y is as a function, what x is as a function of y, and this is the derivative of f. We take determinant and absolute value. This is the sort of the volume of changing coordinates. So let's try to instantiate this formula. Let's do a practice problem here. So here's a problem. So let's say x is a normal distribution with 0 mean and covariance sigma, and the y is the exponential of x. So now the question is, what is the distribution of y? Okay, so let's try to use that formula to try to solve this problem. So how do we begin? So we said p of y is going to be, well, what do we need to find? We need f inverse of y, right? And we need df dx. Those are the two terms we're going to need. So what is f inverse of y?
Log.
It will be log, yes. When I write log, it means base e. Yeah, base e. Log of y. Sorry about that. Okay, good. How about df dx? Yeah, it's just dx of x. Okay, and now we're almost, what is px of x? What is the density of x?
It's 1 over sigma square root of pi.
Yeah, I like to put the sigma squared inside, but yes, that's the same. Okay.
And e to the power, or exp, in parentheses, 1/2, in parentheses, x minus x over, but u is 0, so x over sigma.
Okay, so this is px of x. Okay, I think we're pretty much ready now. Well, let's see one more thing. What is the determinant? Yeah, what is the determinant of df dx?
Itself.
It's still x because it's just scalar, yes. If it was a matrix, that's when we would need this determinant. Okay, and then finally, what's the absolute value of this?
Itself.
It's, exponential is always positive, so this would be just exp of x. Okay, and then, right, so then py of y, so the density of y is 1 over, let's call this term here j of x. So this is 1 over j of f inverse y times px of f inverse y. So that's the new density. So let's plug in, or I think you pretty much see it. So now, what is this term, f inverse y of j? What would that be?
Just y.
Yeah, it will be just y. Like we take log of y and we plug it into its exp, so we have exp of log of y. So this will be 1 over y, and this term will be what? Whatever we have here, we just need to plug in log y. Does this make sense?
Yeah, I think. Okay, so I get the left term, and then f prime of y just needs to be. Is that f?
F inverse, sorry.
Oh, okay.
F inverse, which was this, yeah.
Okay, so you plug that direct in. Okay.
Yeah, we plug this direct, so let's write it out. So we just get 1 over y times 1 over 2 pi sigma squared exp minus 1/2 log of y squared over sigma squared. So something like this. So it's no longer normal, it's some weird distribution, but that should be it.
Okay.
Does this make sense?
Yeah.
I think there's another way to find it, but it's sometimes not easier than this. I think this, at least in most cases, this should work. Questions on this, and I'll mention a few more things.
Yeah, wouldn't allow people just think just to like make everything in terms of something we know, find the CDF, and then convert back to the TF.
Yes, exactly, that's the other way. Yeah, you can do it the CDF way, but then in the end you need to take a derivative, which maybe is not
That's
right.
true, yeah. That's
Yeah.
Okay.
Yeah, I'm gonna show the CDF way as well. Maybe intuitively that one is easier, but it involves differentiation in the end. Questions on what we did here? And if not, we can try one more way. Okay, let's try one more way. So, yeah, so this is the derivation, and I hope we got it correct. Yeah, so we got it right. So it's log squared of y, 1 over y. Oh, I guess we have to check the limits as well in this case, but I don't think we care about the limits. Yeah, we care where it is defined, so we should check the limits as well. Anyways, so let's try the CDF way. So we know that P of x less than or equal to x, this is the Gaussian CDF, right? Now we can substitute for y, so we know that, so to find the distribution of y, I need to find fy of y, which will be, I guess, P of y less than or equal to y, something like this. So how do I go about doing that? I can start with this one, which I know, but plug in the relationship between x and y. I know that x is just log of y, right? So I can rewrite this term here as p of log of y is less than or equal to x. And we can take exponential on both sides, and we get that p of, I guess, y is less than or equal to exp of x. Yeah, so essentially we know that this is just the normal, yeah, this is the normal CDF. So this is equal to, I guess, x. Yeah, but then you, yeah, I don't know, I think it's more confusing this way.
Wouldn't you basically plug in the condition into the probability of x, so make for the probability of x less than the log of y, and then you know, solve from there using the PDF or the CDF of x?
Yeah.
Yeah, that's what I was going for, because this is the CDF of x evaluated at, wait a second. Oh yeah, we could have started that way. Yeah, actually you're right, that would have been easier.
Wait, why is the
Sorry, yeah, what I did was confusing. Let's do one more try, okay?
that was exp of x.
Yeah, this is exp of x, is less than or equal to y. Then let's take log from both sides, it's monotone, so it's not gonna change the inequality. So we have x is less than or equal to log of y, so this is f of x evaluated log y.
And then you just do chain rule, and then we get exactly what we get.
And then we do chain rule, and then we get exactly what we get. Exactly, yes. So then the CDF, this is the CDF of y, so the PDF of y is the derivative, so let's call this fy here, of y. And so this is the derivative of fy of y with respect to y. So that will be, by chain rule, right, it's gonna be dx of fx divided log y times what? Dx dy, right?
And then it's just one over y.
Yeah, dx dy, is that 1 over y?
Yes.
Yeah, it should just be
Is it
Yeah, that's right. Yeah, that's great.
Should it just be like the derivative of log y? Because that's changing.
Depends on what we are. Oh yeah, maybe we don't need to do the chain. Yes. Wait, good, yeah, I agree. Yes, you're right. So this will be, yes, by the chain rule, this will be PDF of x evaluated log y times d log y dy. Yes, sorry about that. Okay, this is correct, yes.
That makes
Okay,
sense.
this is the CDF way, yeah. The CDF way does not always work as ECD. I guess the other formula is more general, or it should work. Like if you have some higher order thing, that's in this thing is where the Jacobian will show up. Probably. Yeah.
So I guess one of my biggest sticking points on this problem was I was getting confused because like I did see this example or like what you showed us and like I mean like you explained it more thoroughly, so thank you. But we only have 2 random variables in the case that you showed us, whereas here we're dealing with 3.
Oh,
And it's
when
almost-
yeah, good question.
Yeah.
When you're computing the observation model, we're conditioning on x. So x,
Okay.
you should not think of it as a random variable anymore because it's conditioned. So you only have 2, it's v and z.
Okay, that's why Hanwon was saying that. Okay, because he was saying that like we're given the probability distribution function for v, and we're gonna need to use that in our answer or something. And I was like, I couldn't see how we were supposed to use it, but it's because z and v are the random variables in this
Yes,
case.
v and
Okay.
v are the random variables, and their relationship is through a constant only. So we're just scaling v by x, which x in this context now will be constant. It's
Okay.
like dividing v by 3. So
Okay.
it's always like asking you if you can answer, here's a sub question that should be easier and you can answer. Suppose let v have an exponential distribution with rate beta. What is the distribution or the density of v over 3? Okay, if you answer this, you pretty much solved. Our problem is v over x, yeah,
Okay.
where x is constant.
Okay. Maybe. Let's see. Wait, am I supposed to answer that?
Oh, no, no.
Oh, okay, okay, wait.
This is the homework problem.
Okay, okay, gotcha. Okay,
Yeah, and our
Note
problem
taken.
is v over x where x is fixed.
okay. Gotcha.
Okay, just to make sure that people are have thought about this. How about the first part of the question? The question asks 2 things, right? What is the function h, and what is the density? What is pH and what is h?
Oh,
So
yeah.
what is h?
Is it not VT over XT?
Yeah.
Okay, yeah, that's what I figured.
So
Okay,
that's- the first part is kind of a trick question. It's
Yeah.
trivial. There is no trick there. It's just v over
Oh.
x. Yeah.
I was confused on that for a while. I'm like, wait, what? Isn't it given? Okay,
It's just v over x. So,
Okay.
so h is clear. Sorry.
It is just the jet observation visible.
Yeah, that's the observation model. Yeah. Okay. Other questions?
I mean, could you give us? Because I'm assuming part C is the same, where we have to do it
Yeah,
for the
part C
motion
is the
model.
same idea, yeah.
Part B though, I didn't really understand what it was asking us to do. It's something to do with like the initial at t equals 0 variables.
Okay, so let's see. What is the probability density function of the room state conditioned on the first measurement z0? Okay, so what is part B asking you to do? Anyone want to guess or help? Say again.
The
Update step. Yeah, we need to do an update step, right? We are given a prior distribution of x, which is lambda e to the minus lambda x. In part A, we're computing the observation model P of H, P sub H.
Right.
So we have prior and observation, and part B is asking you to compute the posterior. So essentially x0 computed on conditioned on z0.
Okay.
How do we do this? With Bayes filter update step or Bayes rule. Yeah.
Okay.
So what do you need to compute then? What should the let's switch back here. Right, so let's talk about part B. So I'm gonna assume P of X is the prior and PH of Z given X is the observation model from A. Then part B now is asking what is P of X given Z, and what should that be? So Bayes rule update step, what is it?
P of z given x
Yeah.
equal to px very
Yeah, so it's gonna be pH of z conditional x times px, and we need to normalize. So I think, I forgot for our problem if it's hard to do or not, but yeah, it's essentially proportional. So the way I would compute it is take the product of these two and make sure that it integrates to 1. If you want it in explicit form, we should do this. So we should divide by the integral of the numerator to make sure that it integrates to 1. So it's going to be pH of z given s, ps ds. I don't remember in our program if this is hard or easy to do. Probably not hard. Yeah, but you need to make sure you find pH first, which is part A.
Okay.
Does that make sense? Yeah, so you just need to do this computation. So multiply the two pHs and normalize.
The P of X, is that coming from
That's given.
the
That's
motion model that they gave us, or?
Yeah, P of x is lambda times e to the minus.
Oh, that, okay.
Yeah, P of x.
Oh, yeah, sorry.
is, this term, lambda e to the minus lambda x. Yes.
Okay, gotcha. So it's a direct, like, plug-in with Bayes' rule, basically, okay,
Exactly.
Gotcha.
Direct plug-in with this rule. Yes.
okay,
Where this is the prior and the observation model is for part A. Yeah.
okay, gotcha.
And C and D are the same idea, but for the motion model and the prediction step.
Okay,
In
gotcha.
this case, we first do update, then prediction,
Mhm.
but the equations are the same. Yeah.
Prediction up there, okay. Thank you.
Remind me what S is in the normalization constant law.
Oh, it was just a variable of integration, so it's a dummy variable. Yeah. So I was just, I mean, it is x, but it's what I'm saying is integrate over that variable. So whatever expression for the function I get, it would be use s and integrate over the range of x. Yeah. Which
That the proportional way that you're talking about is it's basically just like making sure that the integral of a constant times the probability equals to 1, basically.
oh, for this part.
Yeah, because you're saying like, oh, you don't need to calculate the normalization term where you could just say the posterior is proportional
To
to.
this,
Yeah.
yeah. Oh, I see. So you're asking what is the proportional?
It's basically something like an integral of a constant times your like phzx times px
Yeah.
is 1, right?
Exactly.
Okay.
Exactly. Yes. Exactly. And that constant is exactly this actually.
Right.
Yes.
So the probability of x given z should be a function of z, right? Function of z.
The probability. Sorry, which one? P. This one. Z given x.
No, the overall probability of x given z,
Yes.
that should be a function of g. But I'm getting the function in terms of x.
Sorry. Function of z. If you have a function of z, right?
Yeah.
Oh, yes. It should be a function of z for sure. So you're getting something that only depends on x and not z. It's strange because, well, this thing should depend, this is where the dependence on z comes from. So what was your expression for pH, I guess? Does that depend on z?
No, it's v by x.
Okay, but that's not the pH, that is just h, right? So this part A. So we first need to solve part A. So in part A, we know that h x and v is v over x, right? But we need to find what pH is of z given x. So that's the problem that Dallas was asking about, yeah. So yes, your p, so this term should depend on z. So yeah, as we said, we can either use the change of density formula or we can do the CDF way. Let's give a suggestion for the CDF way. So right, we are trying to do z is less than or equal to z. This will be the CDF of z. So let's plug in. So it's going to be v over x less than or equal to z, which is p of sorry, writing twice. V less than or equal to x times z. So this is the CDF of v evaluated at xz. So if we call this function f of z, then we know that pz of z given x, which is the function we want, yeah, I guess this is conditional x here, is z. Yeah, so you can plug in this way and find the derivative with respect to z. That will also give you the answer. So two ways, either the change of density, or if you find the CDF of v, you just plug in xz and take the derivative with respect to z. That will also give you the right answer. You could even do both and compare, make sure that they agree. Did this help?
Yeah.
Okay, more questions? Yes.
Just to clarify a small thing over there, there's a capital X, and I think when you move it over to the right-hand side, it was small.
Oh no, it's everywhere it's small, sorry about that.
So this case, since it's like given X.
Yeah, it's conditioned, yeah, it should be
So it's like we know what X
conditioned.
is and we didn't.
Yeah, okay, the exact right thing. Okay, let me be slightly more formal. I know we're not in probability class, but we should still be formal. So let's see. So it's P of Z capital, it's little z, and we want to condition this on capital X being some little x. So this is then capital V, which is the random variable, divided by capital X, but we're conditioning that the capital X is the little x. Okay, so we can then write this as V less than or equal to Z little x, condition x equals x. Does this make sense? Yeah, so we're assuming some value for x is given. Okay, more questions? Problem one or otherwise? Yes.
Okay, I mean, I'm still recatching up on the lectures for EKF, but like any tips on 2 and 3 that we might need, like things you should know before entering.
Yes. Yes, so problem 2, there are all parts, but I don't think they're too hard. Yeah, the only thing you need to know for problem 2 is some review on how to compute mean and variance, as well as the prediction step of the EKF. You don't even, there's no update here.
Okay.
You only need the EKF prediction step and how to compute mean and variance. Those are, I think, the 3 things you need for problem 2.
Okay.
I'm happy to answer a more specific question, but in terms of what review, that's it.
Yeah. I'll be able to ask more specific stuff
Let's
soon.
see, problem 3. Part 1 and 2 should be trivial.
Yeah.
They're like an exercise you should be able to do right away, because this is stuff from lecture 3. So A and B are stuff from lecture 3. Part C is what we discussed today.
Okay.
Part C is how to do this Riemannian gradient computation. So that's the only tricky part in C. So for that, you can review the example we did in class today first with how to find the derivative with respect to R,
Okay.
and then try it for this function as well. But the function is not hard. Our function is pretty simple here. So in a way, it's simpler than the one we did in class. Yeah.
Cool. Thank you.
So here the psi cap we will derive from the E1.
Say again.
Like say in the class we did for the psi. So that psi cap is the E1, like psi is the E1 here. Yeah, that's the last part I talked about, right? Is the perturbation with respect to psi or with respect to delta theta? I'd say whichever one you do is okay, as long as it's correct, yeah. So you can do it exactly the way we did in class. Maybe I should have changed, yeah, so you can also reinterpret this as the Riemannian gradient or the gradient of E1 with respect to R. That's also okay. Whichever one you do, either with respect to theta or with respect to R, as long as you do one of those correctly, that counts. Yeah. Okay, more questions? We can do more exercises if that will help. Or we can do another Riemannian gradient computation if you guys want to try another one.
You said that'll help us out with number 3, like the Riemannian gradients? Yeah, sure.
So let's do one very simple just to make sure you guys understood. Let's do a very simple one. Okay, let's say we have f of r is rx. Okay. What is the
This is better now. Let's see. Which is fine. Yeah, okay, let's try this one. So, as a warm up, what's the derivative with respect to x? Just as a warm up.
It's R, yeah.
It's just r. Okay, good. How about with respect to r? So, what is grad with respect to r of f of r? What was our approach?
Do you want us to do the perturbation method?
Yeah, let's do the perturbation method.
Okay.
So what should we do?
So we're gonna say R is equal to some R times an exponential, yeah, phi hat.
Yeah, you can use some letter which determines our perturbation. Okay. What do we do next? Yeah, we said psi is some small thing, so we can approximate the exponential with
Yeah.
I plus psi hat. Okay, then I saw the right motion. That's right. Okay, let's multiply out. So we get Rx plus R psi hat x. Okay, this here is this was actually exactly right. So this here is f bar, right? And how about this term? We want to make it what? It needs to be linear in psi.
Minus that.
So we use the same trick we did before, right? The minus for the hat. So it's minus r hat x times psi. Okay, so then what is grad r of f of r? Is the transpose of this, right? Okay, so let's do it slowly. R transpose, right? Let's try to do the transpose. So it's going to be R hat transpose with a minus R transpose, something like this. Okay. Can we simplify this further? What's the transpose of x hat? Yeah, and transpose of x hat is minus x hat. Why is that? It's Q symmetric, yes. Okay, good. Okay, so the minus and the transpose go away, so we're left with x hat R transpose. Yes. Okay, so this is the gradient. Yeah. Did this make sense for everyone? Should we do more examples? But yeah, all of them are like that. You plug in exp of psi hat, you approximate with identity plus psi hat, and then try to simplify to get it to be linear in psi, whatever is left. That's the Jacobian.
So that's the answer.
That's the answer for this problem.
Yes, so the other term x is like even and then r vectors.
I don't know how that Okay, should we do more?
Professor, real quick on that last one, when you say you want to linearize it, your goal is to get it in a sum of terms where each term is like a product?
I want to get it to something that, so I start with a function f of r, I do the perturbation, and I want to get it to something that looks like f of r plus something times psi. So the something here is gradient of f transpose.
Okay,
So whatever the something is that multiplies psi, that's the gradient transpose.
okay,
So I need to get it in this form, something that's multiplied with psi, and something that's just f of r.
okay,
And if there are terms that are psi squared or higher, I can ignore those. So we assume psi is small, so psi squared is even smaller. So in the Taylor series, we can ignore these. The
gotcha.
reason why we can ignore this is that in reality, we're going to take a limit as psi goes to 0, so all these terms will go away.
Like drop off, yeah, okay, gotcha. So go for that form, I'll keep it in mind.
Yeah, so maybe to show this even more precisely, we have this, right? Let's do it like this. T times psi hat, if we can get it to look like this, right? Plus, let's call this G transpose T times psi.
Then when we're taking limits, right, we know that the gradient is gonna be limit as t goes to 0 of this thing here minus f of r divided by t. That's by definition of the derivative, right? So when I plug this in, I'm going to be left with g transpose t side, and when I divide by y. I guess we should have something is off here. We're going to get g transpose t side or t limit is equals 0. No, this should have been. Yeah, this is the directional derivative in the direction of psi. So the overall gradient is just g transpose. Yeah, but this will give us gt psi. But this is the directional derivative in the direction of psi. So this is the gradient. Anyways, yeah. So the term that's linear in psi is the gradient transpose.
Okay.
Yeah, let's do one more. Let me think of something. That would be easy, but yeah, I don't know. Now I'm making a problem, so this could be hard. We can try exp of t z hat t inverse. Okay, so I have some angular and linear velocity, some generalized velocity zeta. I apply this operation t inverse to convert it to a different frame. So this is the world frame velocity, something like that. And I take the exponential map, so it's some rate of change in the world frame. I made up this function. So what's the derivative of this with respect to t? Okay, should we try this one too? So how do we go about it?
F of t exponential side.
Yeah, approach is the same. We should now remember that psi has a slightly different meaning, right? Now it's a 6-dimensional thing, so we're working with poses, and the hot map is the one for 6-dimensional, but the approach is the same. So we would plug in, right? We got exp of t of exp of psi hat, zeta hat, and t of exp of psi hat, and then inverse. Okay, then we can do our simplification like before, right? This is approximately exp of t of I plus psi hat, zeta hat, t of I plus psi hat inverse. Yes. Okay, makes sense so far? Okay, then let's keep going. Yeah, we picked a quite one, but we can simplify. Let's see. Yeah, let's go slow here. So we have t I plus psi hat. Let's just deal with the inverse. So when I take an inverse, it's the same as I plus psi inverse times t inverse. Right, the inverse of a product is we switch the order of the inverses. Then yeah, I'm not sure if we've proven this, but you can show that this is the same as this. I guess the way to try this is to multiply them out. We are going to get something that's second order, or let's say it's approximately this. Because why is this? If I do this and this, I get what? I get identity minus psi hat squared. And we said square terms, we're going to think of them being very small. So we can say that the inverse of this is approximately this, so I can simplify this as well. So I can do t I plus psi hat, c hat
I minus, so I had T inverse. Okay. Now we need to simplify further. Yeah, let me know if you're not following anything, we can go slower. Now we should expand the parentheses in here, so we get exp of T zeta hat T inverse plus, let's say, T psi hat zeta hat T inverse plus T zeta hat okay, this was a relatively hard example. T inverse, and there's one more term, let's see, there's a minus T zeta hat T inverse, something like this. Did I miss anything?
No, I was saying because psi 2 times like that can be negative.
Yes, we probably can ignore this term. Yeah, let's keep it for a second to make sure. But yes, you're right. These are the ones that look linear. Right. So again, we have. Let's see. Yeah, we can proceed in a bunch of ways here. Yeah, we can probably ignore the second order term. Yeah, which I think is fine. Let's keep going. So we got exp of T zeta T inverse plus, what did we have? Yeah, these two terms are pretty fine.
Maybe change the order of psi cap and zeta cap here.
To make those two terms look similar, right?
Yeah, and then add it.
Yes, so we can, but we have to now be careful again, because this is the hat map for R6, not for R3. So we need to check what the properties are. So the properties we know are for the R3 case. So for R6, we didn't cover them in detail. So I guess on the exam, on the final, I'm not gonna ask you a question with poses, but for the purposes of this exercise, let's see what they are. So for poses, you have the expressions here as well. So we can go back a little and look for that. Yeah, so for poses, you have properties like these. Let's see which one we want. Can you guys see this? Let's see if any of these are useful. Yeah, I'm not sure how to unify those two. Yeah, we might not be able to simplify this. So that is actually the Lie bracket on the post group, which I think is fine. I didn't mention that. Yeah. So the term we have is something like this, right? We have zeta hat times or psi hat times zeta hat minus zeta hat times psi hat. So this is actually the Lie bracket on the post group, which is some weird thing here we haven't really defined. But yeah, that's actually yeah. So there's for the poses, there's also something called a curly hat that looks like this. So it's tail hat, row hat, tail hat. So this expression that we got there is actually this. This is the Lie bracket. So let's use it. I guess go back to our slides. Yeah, so I think here we get something like T bracket between psi and zeta, T inverse, and we had some second order term inside, which I think we can ignore. Okay, we got this, and now we still need to linearize this first part in EXP. So yeah, I think this problem turned out to be a little tricky. So this expression here is also small in zeta, inside. So for example, we can use BCH to make things smaller here. So by BCH, we know that this is, actually, let's do directly, let's do BCH. So by BCH, we know that this is approximately, I'm going to ignore this term and leave us with this, the right Jacobian on SO3 times this. Okay, so this for sure is a harder example than we'll ever have in the class. But we get to something like this, and then we should simplify. So this term is still small, so we can approximate this with exp of small is about identity plus small hat. Oh yeah, that one is like a hat, yeah. So in the end, we're gonna get, okay, I'm going a little fast now because we said, yeah, this will be approximately I plus JR T zeta T inverse. So in the end, we get this to look like, this is the original function we started with, ft, plus we have exp of t zeta T inverse times JR T inverse, and we're almost there. Now, this, this is almost the gradient. We need to make it linear inside. So we will need to use a little more properties of the bracket here to get it. But this was I guess this is a hard problem, or a harder version of what we will see. Yeah, so you can expect problems of, yes, we'll probably have some problem on finding derivatives. It will be with rotations, not other things. It will be a scalar function, and yeah, the steps are plug in the perturbation, approximate with I plus psi hat, and then try to simplify to get linear inside. Yeah, I'm happy to finish this if you guys are interested, but yeah, I think the next step would be to know that this is something like zeta curly times psi hat. Then you need to know one more thing, that T psi hat T inverse is like inverse. Yeah, it's a little complicated. Use more properties. This is the adjoint map we had seen for rotations. Remember, this was the way to change velocity from one coordinate frame to another. There's the same thing for poses, so this represents the adjoint, so it rotates velocity from one frame to another with this pose. So you get something called the pose adjoint. But yeah, outside of scope what we mentioned. If you're curious to know more about this, I would say check you don't have to do it before project 3, so focus on homework 3 and project 3. Do the final, and if you're still want to come back to this, review more of the slides in lecture 11, as well as check our book. So in our book, there's chapter 7, which shows a lot of properties of these poses and groups. I'm happy to answer other questions. I don't know, was this example useful or it became too messy at the end? All right, the beginning at least was useful.
Yeah. The steps are in here now, so that's good.
Other questions? Yeah.
One thing about and just in general about symmetric analysis, we have an expression like minus x hat transpose I transpose. We were solving earlier.
Yeah.
And now we can simplify this because R is symmetric. So in this case,
X hat is symmetric, yeah.
oh, okay. X hat is symmetric, so I was I think I didn't quite follow how you got to that expression with this X hat.
Oh, yeah, so Q symmetric means what? The x hat transpose is equal to
Negative.
negative x hat, yeah.
Oh,
So
okay.
I just plug x, so we have minus minus, it gets x hat.
I can't express it with R instead of X, no.
Oh, I see. No, R is not Q symmetric, right? We know that. Yeah, R transpose is just the inverse of R, but it's not minus R. Yeah, R is not Q symmetric.
Yeah, so I'm a bit confused for the all terminologies about the groups. Could you go over it again?
The terminology about the groups.
Yeah, like the manifold, like the relationship between manifold and the tangent plane and the group, the algebra, stuff like that.
Yes, yes,
Yeah.
I should simplify this lecture a bit. I wanted to give you the bigger context, but I feel like it's too much. We should maybe only talk about the groups. But okay, a manifold is, in general, is some curved space. A Lie group is a special case of a manifold. So a Lie group is a kind of a manifold, but there are other manifolds which are not Lie groups. Okay, so if I have the space of manifolds here, and then I have the space of groups here. So a Lie group is right here. And then a subset of this is a matrix Lie group. Okay, so really, when I started introducing stuff, I was talking about this, but in the rest of the things, we were only talking about matrix Lie groups.
Oh.
Okay, so matrix Lie groups is a subset of Lie groups, which is a subset of manifolds and groups. Okay, so actually the gradient descent algorithm we derived works for all manifolds, but a lot of the properties we looked at for distance and integration and so on only works for matrix Lie groups. So I would say whatever we said is pretty much for matrix Lie groups, but the gradient descent algorithm we got actually works for any manifold as long as you can get the gradient. So then let's see, what else did we say? So we said for a manifold, there is, for every point, P on the manifold. So if I have P on the manifold, whoops, let's go to manifold M. We said there's some chart that defines a little neighborhood U, function phi, which essentially takes points from this neighborhood and maps them into something like Euclidean space. Okay, so for any point we can assign, so this is called a coordinates function, f of p are called the coordinates of p, because now think of this, in Euclidean space we know how to give coordinates. I have an x-axis, a y-axis, a z-axis, I can locate points. On this curved space you don't know how to make your coordinate frames, right, because everything is curved. How do you define coordinates even, right? So the definition of coordinates here is f of p, or any point around P here. If I take this point, let's call it Q, its coordinates are f of Q. Does that make sense?
Yeah, so let's say if I want to move in the chart space, right? So let's say from point P, is the point P the center of that chart?
Yeah, it doesn't have to be, but yes, the simplest way to think about it is that, yes, P is the center and the chart is some region around it, yes.
Oh, so like let's say if I move from point P to some like other distance inside the space, then does that mean I basically the math is phi of P plus the new coordinate in that RD, and then we use the phi inverse to map it back to the manifold?
Pretty much. You have to be careful because when you move on the flat space far, your mapping back to the manifold might not be phi anymore. It might start to, well, it depends. If you stay within it, so the region of RD, which is associated with U, is it's not all of RD, I guess. It's some little set here.
Yeah.
So if you go outside of this set, you need a way of coming back.
Just a really small step is valid, right?
Yeah, really small step is valid. So let's do this in the context of Lie groups because it's a little bit easier. So for Lie groups, you can define, let's see. So let's even do it for rotations because I think it's easier to understand. So let's say we have some rotation here. We can find the associated flat space here, and it looks like this. Let's see what the coordinates are. Yes, so points around R, so our little U set, for example, are points around R of this form. Let's go with psi actually, so we've been using that. For psi is in R3. Or let's put this another way, or the phi function, yeah, so phi of R is actually, yeah, one choice for phi of R will be log of R, which is some function, yeah, which is theta. So the chart, log v of R gives you the, so the coordinates of R are the axis angle. Okay, this is in Euclidean space, right? It's three-dimensional. And then the little region around R, you can think of it as essentially some perturbation around R. So if I take a step in the theta space, it's like I'm adding some little psi.
Yeah.
In the theta space, it corresponds to perturbing R this way.
Oh. Yeah, so that is basically what the Stack Overflow for Project 1 is talking about, right?
Yes, exactly.
That's
So-
exactly the thing.
Right, so let's see if I can go to the picture. Yeah, so this point here gets mapped to theta. And then points around, so let's say we want to perturb theta to something like theta plus delta theta. So I generate some little perturbation. So then the corresponding, and then I want to map back. Right now I want to find a point that this maps back to, so I need to take something like exp of theta plus delta theta. That would be the new rotation, and we know from BCH that this is about r times exp of jr times delta theta. So that would be the new. So if I move in this tangent space, I'm going and apply exponential. I'm going to get back to a point that looks like this. So for rotations and Lie group, matrix Lie groups in general, we always work with the Lie algebra instead of the tangent space because we can always translate there, and instead of thinking of theta as the center is just zero. So I can force my coordinate system to be around zero because I can always, instead of thinking about what happens around R, I can always rotate to zero to do the move there and rotate it back. So that's why we define the Lie algebra as sort of a special tangent space, but really it just says, instead of having your coordinate system centered around theta, just center it around zero, do your perturbation or whatever, and then to return back to R, you would just, whatever your perturbation is, you just multiply on the left with R, and that was like shifting it to the location of R.
So can I consider like the Lie, is that Lie algebra basically the origin of the manifolds, like a bunch of
Yes, the Lie algebra is the tangent space at the identity of the manifold, and the identity of the manifold is the identity matrix, yeah.
Oh,
So the Lie algebra is the tangent space at identity, exactly.
got it, thank you.
Could you repeat the algebra is the tangent space of the identity?
Yes, so it's the tangent space around, so we can have a tangent space around any point of our manifold, so around every rotation there's a tangent space. Around the one around the identity rotation is the Lie algebra. So they look like this, I don't know if I have it in the slides, but they look like this. So the tangent spaces, let's call it T, R, M. So it's the tangent space of the, oh, it's not M, it's SO3. So the tangent space of SO3 at rotation R looks like this. Okay, and the the tangent space around the identity, obviously, looks like this. And this is what we call the little SLP. Does this make sense? Yeah, so we work with the Lie algebra because it's just omega hat, while the other tangent spaces are like translations or left action on omega hat. So in a way, they're all equivalent, right? Which, if you want to work on the tangent space in some particular rotation, is the same as working in this Lie algebra tangent space, and then multiplying with R will get you back to that. So in the case of a Lie matrix Lie group, converting between the tangent spaces is easy. That's why we define the Lie algebra and only think about it, because we can convert between the tangent spaces. So they always look, even if we had poses, right? The tangent space around the pose T of, let's say, SE3 looks like T times, say, a hat, for example, something like this. Say a hat is in R6 here, and little SE3, which is the tangent space around the identity of SE3, is just Z hat. So again, instead of thinking of the tangent space right here, you can do things in the Lie algebra and then multiply with T is the same result. That's why we define Lie algebra, not to think about tangent space. But if you have something that's not a Lie group and it's a general manifold, this relationship is not as easy. Like converting from one tangent space to another gets more complicated. So in general, this might be more sophisticated. But in our case, when you have a Lie group, you can always work with the Lie algebra because converting between the tangent spaces is easy. Okay. Questions? Other questions? Yes.
Can you go over slide 11 with EKF? Just kind of like what, specifically what f of mu ut in 0 is?
Sorry, slide 11 in which lecture?
10.
Or lecture 10 or 11?
10.
10. Okay. Slide 11.
Yeah.
Ah,
So
okay.
like the formula is at the top. Like, what exactly are we taking the derivative of when we're calculating ft and qt? Just like the normal.
We're taking the derivative
Yeah.
of f. So f is the motion model. So depending on the problem that we're assuming that's given to us somehow. So for example, if f was the yeah, let's switch back here. Yeah, so let's say we had a motion model. Let's take some subset of the differential derived motion model. Let's say it was our motion model was xk plus 1 is xk plus vk cosine of theta, for example. So let's say this is f of should I call this? Let's call p. So this is f of p theta is, let's say, x and v. And then we need to have some noise. Plus, let's say w, yeah, we can use t. Sorry, let me simplify this a little further. Yes, t, let's say this is u, this is t, and this is t plus 1, maybe something like this. Yeah, I'm going to pretend that theta is given, so our model is a little bit simpler. Okay, so this is a motion model of P, U, and W, okay? Which is, oh, it is actually linear now. Sorry, let me add a little more to it. Theta t plus 1 is, let's say, u1 t and then u2 t, something like this. Okay, so let's say this is our noise 1t and then noise 2t. Okay, this is our combined motion model. So let's call x is p and theta. So then we have xp plus 1 is f of xp, t, and w. Okay, does this make sense? So I define some motion model, it's defined by these two equations. So what that corresponds to is we need to find the derivative of the motion model with respect to x and with respect to w. So let's do it. So what would be the derivative of f with respect to x? Okay, you guys help me. So let's do it with respect to p first.
It would just be 1, right?
It will be 1 on in the first equation, and how about in the second? 0. And how about with respect to theta? U1 sine of theta with a minus, and 0 here. That's right. How about the dw? This will just be identity. It's 1 0 for with respect to w1 and 0 1 with respect to w2. So those are the things we are calculating, and then what we're saying is we need to evaluate this one at the mean. So if we have some distribution on x that, let's say, it's Gaussian with mean 1 2 and covariance, let's say 2 identity, then I will need to evaluate this Jacobian at theta equal to so p equals 1 and theta equals 2. So when we compute the Jacobian, it can still be a function of p or theta. So to use that in the Kalman filter, we evaluate it at the mean. So I would plug in 0 for omega and the mean for x.
Okay, so in relation to the homework, once we take the derivative, we're evaluating it using the previous mean we calculated.
Exactly.
And then, when finding variance, should we do it using the covariance formula, or should we do it using like standard mathematical variance as
I think we should have
expected
all the
values,
equations derived in this lecture 10. So you don't need to derive how to compute the variance again.
Yeah, should we use the covariance formula, or is there?
Yeah, just use the covariance formula.
Okay.
That's great. Right, so the covariance should be for the prediction step is this one, and for the update step is this one. Yeah, so these formulas you can use directly.
Okay.
You don't have to justify them with direct them. I really need to go. I can answer one last question and only a quick one. I think somebody wanted to ask a question there, but okay, no more questions. Okay, I need to go.